Section: Introduction. In this section, we introduce vector quantization, which helps us discretize a continuous vector space. It involves defining a limited set of vectors, known as the codebook, and mapping any vector from the continuous space to the nearest codebook vector. However, training deep learning models that utilize vector quantization can be challenging because the process of replacing a vector with its closest codebook counterpart is not differentiable. This characteristic was not a concern when vector quantization was first developed for applications like noisy channel communication, but it poses a problem in deep learning since gradients cannot flow through layers that use vector quantization during backpropagation. In deep learning, vector quantization is primarily used in the vector quantized variational autoencoder, or VQ-VAE. This model includes a vector quantization layer between the encoder's output and the decoder's input, which quantizes the learned representation. While VQ-VAEs are widely used in advanced generative modeling, the gradients cannot flow smoothly from the decoder to the encoder because they must pass through the non-differentiable vector quantization layer. To address this non-differentiability, we can use a method called the straight-through estimator, STE. During backpropagation, the STE allows us to copy the gradients from the decoder's input to the encoder's output, effectively bypassing the quantization step. However, this approximation can lead to poorly performing models and a phenomenon known as codebook collapse, where many codebook vectors become unused. Even if codebook collapse does not happen, the codebook is often underutilized, limiting the information capacity of the VQ-VAEs bottleneck. In our work, we propose a different approach to propagate gradients through the vector quantization layer in VQ-VAEs. For a given encoder output and its nearest codebook vector, we smoothly transform the encoder output to the codebook vector using a rotation and rescaling transformation. We then send this transformed output to the decoder instead of the direct codebook lookup result. By treating this transformation as a constant during backpropagation, we ensure that gradients flow back from the decoder to the encoder without obstruction. We refer to this method as the rotation trick. It does not alter the output of the VQ-VAE during the forward pass, but during the backward pass, it allows the gradient at the codebook vector to inform the gradient at the encoder output. This preserves the angle between the codebook vector and the gradient, which encodes relative distances and magnitudes into the gradient, changing how points within the same codebook region are updated. Unlike the STE, which applies the same update to all points in a codebook region, the rotation trick can adjust the distances between points based on the gradient direction, potentially increasing codebook usage and reducing quantization error. In the context of lossy compression, both of these adjustments are beneficial for minimizing distortion and enhancing the information capacity of the vector quantization layer. When we applied the rotation trick to several open-source VQ-VAE implementations, we observed significant improvements in reconstruction performance, increased codebook usage, and reduced distances between encoder outputs and their corresponding codebook vectors. For example, training the VQ-GAN on ImageNet with the rotation trick improved reconstruction metrics substantially. Next, we review related work that builds on the foundational VQ-VAE research to enhance its performance. We categorize these efforts into two main groups: methods that bypass the STE and those that improve interactions between the codebook and the model. For methods that bypass the STE, some researchers have sought to address the issues caused by it by avoiding deterministic vector quantization. Techniques like the Gumbel softmax trick create a categorical distribution over codebook vectors that approaches a one-hot distribution as training progresses. Other approaches involve alternating optimization, where the encoder is trained to produce representations close to codebook vectors while the decoder minimizes reconstruction loss from a fixed set of codebook inputs. While these methods help mitigate training instabilities, they can introduce new challenges, such as low codebook utilization during inference. In terms of improving codebook interactions, some strategies involve changing how we look up codebook vectors. For instance, using cosine similarity instead of Euclidean distance or employing stochastic sampling based on the distance between encoder outputs and codebook vectors. Other methods focus on the learning process of the codebook itself, such as splitting high-usage vectors, reviving low-usage vectors, or fixing codebook vectors to a predetermined geometry. Some approaches also introduce loss penalties to encourage better codebook utilization. While these methods effectively target specific training challenges, they still rely on the STE, which can lead to ongoing training instability. In our experiments, we implement a subset of these approaches and find that replacing the saint with our rotation trick further enhances performance. Section Summary. In this section, we discuss the challenges of training vector-quantized variational autoencoders, VQ-VAEs, due to the non-differentiable nature of vector quantization, which complicates gradient flow during backpropagation. We propose a novel method called the rotation trick to facilitate gradient propagation by smoothly transforming encoder outputs, leading to improved reconstruction performance, increased codebook usage, and reduced quantization error in VQ-VAEs. Section: Straight-Through Estimator, STE. In this section, we review the straight-through estimator, STE, and visualize how it affects gradients. We also look at two alternatives to STE that seem to improve its approximation. We define a sample space for our input data with a specific probability distribution. For an input, we have an encoder that deterministically maps it to a prior distribution. The vector quantization layer selects the nearest codebook vector to the encoder's output based on Euclidean distance. The decoder is similarly defined and parameterizes the conditional distribution over reconstructions. Our loss function is derived from the evidence lower bound, ELBO, where the KL divergence term is 0 because the prior distribution is deterministic and we assume uniform usage of codebook vectors. We also introduce a codebook loss to help learn the codebook vectors and a commitment loss to align the encoder's output with the codebook vectors. The stop gradient operation is used, and we set a hyperparameter typically between 0.25 and 2. For the predicted reconstruction, our optimization objective focuses on the difference between the input and the reconstruction, as the other terms do not depend on the decoder. During backpropagation, we need to differentiate through the vector quantization function. We can break this down into three parts: the gradient from the loss with respect to the codebook vector, the gradient through the vector quantization layer, and the gradient through the encoder. Since vector quantization is not smooth, we cannot compute the gradient through it, so the STE copies the gradients from the codebook vector to the encoder output, effectively bypassing the quantization. This means that the gradient update for the encoder does not depend on its exact position within the Voronoi partition created by the codebook vectors. We visualize this effect, showing that the gradient field is partitioned into regions, each receiving the same update regardless of the encoder output's location within that region. We then ask if there is a better way to propagate gradients through the vector quantization layer. One might consider estimating the curvature at the codebook vector and using that to adjust the gradient as it moves towards the encoder output. This can be done by approximating the loss at the encoder output using a second-order expansion around the codebook vector. While calculating Hessians for model parameters is often impractical, we can compute them for just the codebook vectors. We can also compute the exact gradient at the encoder output by making two passes through the network. We define two losses, one with vector quantization and one without. By combining these losses with a small constant to scale the effect of the second loss, we can adjust the gradients accordingly. However, since the gradient through the vector quantization is non-differentiable, the gradients from the loss with quantization won't flow to the encoder. Although these methods seem to improve the encoder's gradients, they may actually lead to worse performance. This is because calculating the exact gradient for the encoder output resembles the autoencoder gradient, which VAEs and VQ-VAEs were designed to improve upon. Consequently, using these methods can cause the encoder to behave like an autoencoder, leading to poor generalization and overfitting, as we observe in our results. Section Summary. In this section, we review the straight-through estimator, STE, and its impact on gradient propagation in vector quantization, highlighting its non-differentiability issue and how it simplifies backpropagation by bypassing the quantization layer. We also explore alternatives to STE, such as Hessian approximations and double forward passes, but find that these methods lead to poorer performance by inadvertently training the encoder like an autoencoder, which is less effective than the intended VQ-VAE approach. Section: The rotation trick. In this section, we introduce the rotation trick. We recognize that updating the encoder's parameters by calculating the gradient at the encoder's output can be problematic. The straight-through estimator, STE, seems to lose important information about the position of the encoder output within the quantized region, which does not influence the gradient update. We believe that capturing this information, specifically the position of the encoder output in relation to the quantized value, could enhance the encoder's gradient updates. Geometrically, we explore how to transfer the gradient from the quantized value to the encoder output while preserving certain characteristics. The STE suggests maintaining the direction and magnitude of the gradient during this transfer. However, we propose a different method. We aim to keep the angle between the gradient and the quantized value constant as the gradient moves to the encoder output. We call this method the rotation trick, and we demonstrate in a later section that preserving this angle leads to beneficial properties for how points move within the same quantized region. We formally define the rotation trick for the encoder output. We denote the corresponding codebook vector as the quantized value. Since the codebook function is non-differentiable, gradients cannot flow through it during the backward pass. The STE addresses this by maintaining the gradient's direction and magnitude as it moves from the quantized value to the encoder output, using a clever adjustment in the backpropagation process. In contrast, the rotation trick redefines this process by treating the forward pass as a rotation and rescaling that aligns the encoder output with the quantized value. We define a rotation transformation that aligns the encoder output with the quantized value and rescales it to match the magnitude. We treat these transformations as fixed constants during differentiation to avoid complications. While the rotation trick does not alter the forward pass output, it changes the backward pass. Instead of setting the gradient transfer to be an identity transformation as in the STE, we apply a rotation and rescaling transformation. This means that the gradient's transfer depends on the encoder output's position within the codebook, while the angle between the gradient and the quantized value remains constant. We also note that the rotation transformation can be efficiently computed using householder reflections. We define normalized versions of the encoder output and the quantized value, along with a scaling factor. The rotation and rescaling that align the encoder output with the quantized value can be derived efficiently, which minimizes GPU memory usage. Importantly, we found no significant difference in training time between models using the STE and those using the rotation trick in our experiments. Section Summary. In this section, we introduce the rotation trick, a method that improves gradient updates for the encoder by preserving the angle between the gradient and the quantized output during backpropagation, as opposed to the straight-through estimator, STE, which only maintains direction and magnitude. We also demonstrate that this approach can be efficiently computed using householder matrix reflections, minimizing GPU memory usage without affecting training time. Section: Voronoi partition analysis. In this section, we analyze Voronoi partition analysis in the context of lossy compression. We find that vector quantization is effective when the distortion, or quantization error, is low and the information capacity, or codebook utilization, is high. In our experiments, we will demonstrate that VQ-VAEs trained with the rotation trick achieve these goals by significantly reducing quantization error and increasing codebook usage compared to those trained with the straight-through estimator, STE. To understand why this happens, we examine how encoder outputs mapped to the same Voronoi region are updated. The STE applies the same update to all points in a partition, while the rotation trick adjusts updates based on the points' locations within the Voronoi region. This means it can either push points apart or pull them closer together, depending on the gradient's direction. Pushing points apart can lead to better codebook usage, while pulling them together can reduce quantization error. we define the angle between the error and the codebook vector as theta, and the angle between the codebook vector and the gradient as tilde theta. When theta is large, indicating high distortion, we want the error to either move closer to its current codebook vector or switch to a different one. This is preferable to keeping the error at a constant distance from the codebook vector. We will show that the rotation trick allows for both options, while the STE only supports the latter. When the gradient and the codebook vector point in the same direction, encoder outputs that are far from the codebook vector are pushed further away than they would be with the saint. This is illustrated in our figures, where points with large angular distances move away more than those with small distances. In the top right of our Voronoi diagram, we see that points at the boundary with larger angles to the codebook vector are pushed away, while those with smaller angles move with it. This ability to push points into previously unused codebook regions enhances codebook utilization, a feature not available with the saint. Conversely, when the gradient and the codebook vector point in opposite directions, the distance among points in the same Voronoi region decreases as they are pulled toward the updated codebook vector. This is also shown in our figures, where the rotation trick pulls points with high angular distances closer to the new codebook vector, which helps reduce quantization error. Together, these capabilities create a push-pull effect that meets two key goals of vector quantization: increasing information capacity and reducing distortion. Points far from the chosen codebook vector are pushed into other regions, enhancing codebook utilization, while points clustered around the codebook vector are pulled closer together, reducing quantization error. Finally, we note a difference with the STE when the gradient is exactly orthogonal to the codebook vector. In this case, all points in the Voronoi region rotate by the same amount in the direction of the gradient. Although this situation is rare, the orthogonal component allows points to move in different directions, either expanding or contracting based on the angle. Section Summary. In this section, we analyze how the rotation trick in vector quantization enhances codebook utilization and reduces quantization error by allowing encoder outputs within the same Voronoi region to be updated based on their specific locations, unlike the STE, which applies uniform updates. This push-pull mechanism enables points with large angular distances to be pushed into unused codebook regions while simultaneously pulling closely clustered points towards the updated codebook vector, effectively achieving the dual goals of increasing information capacity and minimizing distortion. Section: Experiments. In this section, we evaluate the impact of the rotation trick on various VQ-VAE models. We previously demonstrated that this technique enhances codebook usage and reduces quantization error by altering how points in the same Voronoi region are updated. However, we are uncertain about how these changes will influence applications. We start with image reconstruction by training a VQ-VAE to reconstruct images from ImageNet, using a training objective that combines reconstruction, codebook, and commitment losses. We simplify our approach by omitting the codebook loss and using an exponential moving average for updating codebook vectors. For our evaluations, we work with input images sized 256 by 256 pixels and test two configurations, one compressing to a latent space of 32 by 32 by 32 with a codebook of 1024, and another compressing to 64 by 64 by 3 with a codebook of 8192. We compare the results using both Euclidean and cosine similarity for codebook lookups. We track reconstruction metrics for both training and validation sets, calculating reconstruction FID and as to assess quality. We also measure codebook usage, which indicates how many codebook vectors are utilized in each data batch, and quantization error to evaluate distortion. Our comparisons include several methods: the STE estimator, Hessian approximation, exact gradient backward pass, and the rotation trick. All methods share the same architecture and training settings, which we summarize in an appendix table. The only difference among them lies in how gradients are handled during backpropagation. Our findings reveal that the rotation trick significantly reduces quantization error and enhances codebook utilization, aligning with our earlier analysis. These improvements lead to better reconstruction metrics, as we observe substantial gains in R-FID and R-IS when using the rotation trick. In contrast, the Hessian approximation and exact gradients yield poor reconstruction performance, likely due to overfitting and poor generalization from training the encoder like an autoencoder. Next, we assess the rotation trick's effect on VQ-VAEs, where the training objective incorporates perceptual loss and adversarial loss. We evaluate VQ-VAEs in two settings, one suitable for autoregressive modeling with transformers and another for latent diffusion models. We provide detailed descriptions of both training settings in an appendix table. Our results indicate that, similar to our previous findings, using the rotation trick in VQ-VAEs also reduces quantization error and improves codebook usage. Additionally, reconstruction performance, as measured by total loss, RFID, and RIS, shows significant improvement across both modeling paradigms. Section Summary. In this section, we evaluate the impact of the rotation trick on various VQ-VAE configurations, including image and video reconstruction, and find that it significantly reduces quantization error and improves codebook utilization, leading to better reconstruction metrics. Our experiments across different VQ-VAE paradigms also confirm that the rotation trick enhances performance, demonstrating its effectiveness in both simpler and more complex models. Section: VIT-VQ-VAE Evaluation. In this section, we evaluate the VIT-VQ-VAE model, which improves upon the VQ-VAE by using a vision transformer, VIT, instead of a convolutional neural network, CNN, for the encoder and decoder. The VIT-VQ-VAE employs factorized codes and applies L2 normalization to both the input and output of the vector quantization layer, enhancing performance and stability during training. We also modify the training objective by introducing a logit Laplace loss and restoring the L2 reconstruction error to the VQ-VAE loss. For our experimental settings, we utilize the open-source implementation and adhere to the default model and hyperparameters for the small VIT-VQ-VAE. Detailed training settings can be found in the appendix. Our results, summarized in a table, show that, similar to our earlier findings with VQ-VAEs and VQ-VAEs, the utilization of the codebook and reconstruction metrics have significantly improved, although the quantization error remains roughly the same. We then extend our analysis to video evaluations, examining the impact of the rotation trick on video reconstructions from the Bear robot dataset and the UCF-101 action recognition dataset. We adopt the quantization approach of VIT-VQ-VAE but substitute the VIT with a time S-former video model. Due to computational constraints, we use a smaller time S-former model with 8 layers, 256 hidden dimensions, 4 attention heads, and 768 MLP hidden dimensions. Further details on the architecture and training settings are available in the appendix. Our results indicate that training a time S-former VQ-VAE model with the straight-through estimator, STE, leads to codebook collapse across both datasets. Despite experimenting with various hyperparameter settings, we find that codebook utilization drops to nearly 0% within the first few epochs. In contrast, models trained with the rotation trick maintain training stability and yield high-quality reconstructions, as shown by the RFVD metric. We also present several unselected video reconstructions in the appendix.